Welcome back to the System Design series. In the last episode, we learned about the various software design models and how we can represent a system using the functional, object, and the dynamic models. So let's continue with our journey, and in this episode, we will learn about system design activities. But before we do that, let's go and learn about software development lifecycle at a very high level. SDLC is a detailed plan describing how to develop, maintain, or enhance a specific software system. The lifecycle defines a methodology for improving the quality of the software and the overall development process. SDLC can have many detailed steps and phases, but at a high level for discussion, we will break down the process into 4 different phases. The requirement collection phase. This is the very first phase that helps us to build the functional model for our system using the use case diagram. The analysis phase. This phase helps us to build the object model for a system using the class diagrams. The system design phase. In this phase, we perform a set of activities in order to define the design for a system. This is where we define the design goals and perform the system decomposition. We build the dynamic model for a system using the sequence and the state diagrams techniques that we learned earlier. The implementation phase. This is the last phase where we take a design and start building out the system. We use the functional model to flush out and build the UI UX experiences for a system. We translate the object model into code by creating classes. We use the dynamic model to define services and interfaces. And finally, we build and deploy all of these to get a system up and going. Let's look into the various activities that will help us build a very solid system design. There are a total of 8 such activities, and generally they are carried out in the above said order. We will go through each of these activities in a high level in this video, and we will review each of them in more detail in subsequent videos. Identify design goals. The first step is to identify the design goals. And if you recall, we had introduced the concept of design goals in one of our previous videos. So if you haven't seen that, I highly recommend that you go and check it out first. We work on defining the functional requirements that will help us understand the functions that our system needs to perform. Then we define the non-functional requirements, which essentially add constraints to our system. The next step, system decomposition. The next step involves decomposing the system into various subsystems. We use the layering and the partitioning principles to divide the system into logical groups. Then we follow the coupling and the cohesion principles to reduce the interdependency between the subsystems, making it more modular and maintainable. Once we have the knowledge of the various architectures like the client-server, peer-to-peer, and many more, we will pick an architecture that best represents a system and our various subsystems as well. We use this architecture to build the various services and components within a subsystem accordingly. Identify concurrency. We look deeper into our dynamic model and find the opportunities for parallel execution. Parallel execution will make our services more performant and reduce the overall processing time for our operations. This is specifically important for a very large system that we're trying to build here. Likewise, we identify the areas of concurrency, that is, the situations where multiple clients update the same resource, and we work on reducing those critical areas to avoid deadlocks. We determine if a service can best be implemented as a process or as threads, as each of these constructs have their own pros and cons. We will cover all of these aspects in detail in our subsequent videos. Hardware and software mapping. In this step, we focus on picking up the right hardware and software that is required to support a system. We perform system throughput, data storage, and bandwidth estimates for a system. We review if some special purpose systems can be used to solve certain kind of problems with ease, thus saving us valuable development time and effort. For example, if we need to cache some data, we may choose not to build our caching solution rather than use a tested solution like Memcache or Redis to cache the frequently used data. Such software can significantly improve the response time for our service. We also review if we are better off buying or licensing certain components or services rather than building on our own. persistent data management. This is a very important aspect, especially for a large-scale system. A wrong choice can cause the system to fail or not scale to the level that we would expect. With a large number of data storage options available these days, we analyze the data usage pattern for our subsystem. For example, are we reading or writing? What is the data retention that we need? What is the required data retrieval speed, and so on. Based on these, we will choose the database that will be used by our subsystem that may range from a file-based to RDBMS or NoSQL solutions. Global resource handling. In the next step, we deal with security and access management concerns. We need to apply such governance at every touch point, both within a subsystem as well as anything that is external to our subsystems. For example, how do we make sure our services are secure? How do we store sensitive data that is at rest? We may rely on creating access control lists, also known as ACLs. These ACLs allow us to protect a resource and define authentication and authorization schemas around the services. Software control. The other area of concern is software control. This helps us to answer questions like, how does the control flow of a system look like? Do we follow a request and response model, or should we use the asynchronous messaging for a system to support our design goals? Do we build a centralized or decentralized flow? As each of these schemes have their own pros and cons. Also at the same time, the choice of programming styles like procedural versus functional can also add some constraints, or it can help solve a constraint depending on a use case. Boundary condition. Once all of these activities are done, we focus on the last step. That is to handle the boundary conditions. The boundary condition represents use cases like initialization, termination, and failure of a components within a system. This helps us answer questions like, how is a system brought from a non-initialized state to a steady state? What resources are cleaned up and which systems are notified upon terminations? How will the system recovery and restart happen after a failure? We have to make sure that a design withstands and take care of all of such conditions. And that's why we have this practice of system design activity. In the next video, we will cover upon the dependencies of the system design activities on each other and how the analysis model helps us uncover all of those. Thank you.